Hello, 5th and 6th grade. Today we're going on to a new chapter in science, chapter 12, and we are going on to astronomy. And so we're going to talk about stars and some other awesome things in our universe. So we are going to be opening to page 140 at the beginning of chapter 12, astronomy. Some vocabulary to start us off is apparent magnitude. Apparent magnitude is the measure of a celestial body's brightness as observed from the Earth. Key ideas that we'll be covering. The Earth is a small yet very significant part of a series of much larger systems. There are patterns and a variety in types, positions, and motions of celestial objects. Stars produce light energy and exhibit changes similar to life cycles. Stars often appear brighter and more numerous when they are viewed from a secluded place like a mountaintop, desert, or rural meadow. Actually, they are always burning brightly, even during the day. Stars only appear more brilliant at night or in certain areas because other light sources, such as the sun, the moon, or city lights, are not overpowering them. The degree of brightness of a star, as seen from Earth, is its apparent magnitude. Since apparent magnitude is based on the perspective from Earth, it does not provide the true intensity of the star. For instance, the sun looks very radiant. However, this is not because it is large or emits more light than other stars. It's because it is closer to the Earth. In reality, our sun is only a medium-sized star. The apparent magnitude of an object is shown with numbers. The brighter an object appears, the lower the numerical value. The fainter it is, the higher the number. Therefore, objects that have negative numbers appear brighter than objects with positive numbers. Our sun has an apparent magnitude of negative 26.7 because it is so close to the Earth. Proxima Centauri, the second closest star to the Earth, has an apparent magnitude of approximately positive 11. So that kind of gives you an idea of how much farther away the next closest star is to Earth. The apparent magnitude of a star, planet, or moon depends on its size and temperature, as well as how close it is to Earth. Quick fact. When photographing distant and faint objects, enough light has to be collected. Astronomers use computer software, special filters, and finely machined gears to focus the telescope on an object while the Earth rotates. To accomplish this, a camera's shutter is open for a very long time, sometimes for more than an hour. Strange but true. What is the name of this celestial body? So if you've ever tried to take a picture of the stars or the moon, it's really difficult to because in normal camera, when you take a picture, the shutter or the part of the camera that opens to receive light and then closes really fast is only open for a short amount of time. So only a small amount of light is able to enter that camera. When you see professional pictures where they have beautiful pictures of the stars or the moon, or if you've seen fast motion videos of like the skyscape over the course of a night or the aurora borealis, and you can see shooting stars and you can see how the stars move over the horizon throughout the night. That's because they on their camera they have a setting that allows the shutter or that little window that opens and closes to stay open for long periods of time. And what happens is as that shutter, you click it, the shutter stays open and it's able to take in all of the light, not only the most bright and apparent light, but even the faintest light from stars from a distance. And then as that shuts and you develop the picture, you're able to see lights that you wouldn't be able to see from a normal quick shuttered camera. It takes a lot of precision. It takes a lot of practice, so you don't get a blurry picture having it open for so long, but it does create a beautiful photograph of what is really being seen, sometimes more than we can see with our naked eye. All right, we're flipping to the next page, starlight. Again, absolute magnitude is the actual brightness of a celestial object. quick fact. The idea of apparent magnitude goes back over a century before Christ when the Greek astronomer Hipparchus ranked the brightest of stars. A magnitude of 1 was given to the brightest stars, and a magnitude of 6 was given to the faintest ones. This original classification is the basis for why greater numbers are used today than for dimmer stars. With today's instruments, decimal numbers and negative numbers can be used to describe wider and more precise range. And you can see on the bottom of the page there's a scale that shows both apparent and absolute magnitudes are calculated by using the same scale. However, the two measurements can be very different for the same object. So apparent, if you think of the word, what does the word apparent mean? It's what we think. Okay, so if you say apparently or what we think, that's kind of like a guesstimate of how bright we think a star is based off of what we observe here on Earth. Absolute means factual, definite. So absolute magnitude would be the actual brightness of a celestial object. So how bright it actually is in reality, not just based off of what we observe. The actual brightness of a star affects its apparent magnitude. Stars shine because they emit light energy. This energy is produced through nuclear fusion, which is the joining together of smaller atoms to form a larger one. The fusion process releases enormous quantities of energy. Starlight is the visible product of the energy released by fusion. Stars that produce greater amounts of energy will usually produce more light. There goes my tea kettle. Now let me read that again. Stars that produce greater amounts of energy will usually produce more light. The actual brightness of a star depends on two main factors, the size and temperature. The larger the star, the more matter there is to burn. The temperature of the star's surface, measured on the Kelvin scale, reveals how much light it gives off. A star's color also depends on its temperature. Hotter stars burn more intensely and are blue or white. Cooler stars burn yellow, orange, or red. So if you think of a fire, if you have a campfire, the hottest parts of the fire, which are usually closest to the logs or the coals, looks like it's white or blue in color, and then the farther the flames get away, the more yellow, orange, or red it is. So the same goes with star. The brighter it is, the more heat it has, the hotter the star is, the more white or blue scale it's going to be than yellow, orange, or red. The absolute magnitude of a star is the measurement of its actual brightness. It takes into account how bright a star is compared to all the other stars, if they were all put on a standard distance of 32.6 light years from Earth. A light year is the length that light travels in 1 year inside an area that contains no matter. Scientists say that this distance is around 9.46 trillion kilometers, or 5.88 trillion miles. Since absolute magnitude reveals the true brightness of a star, it has an effect on how bright the star appears to Earth. Since the sun is a star, will it eventually burn up? Obviously, celestial bodies are not all 32.6 light years away. Therefore, the apparent magnitude of an object can be very different from the absolute magnitude. This is because apparent magnitude is the result of the distance from Earth, and absolute magnitude is dependent on its size and temperature. For example, the sun looks brighter than the star Antares. The sun's apparent magnitude is negative 26.7 as compared to that of Antares at +1. However, Antares is actually a much brighter star with an absolute magnitude of negative 4.5, while the sun is positive 4.8. Yes, Antares does not light up the Earth's sky. This is because its distance from the Earth is about 520 light years away. So if you think of, let's go back to what is a light year, 5.8 trillion miles. Okay, so that's 1 light year. 5.8 trillion miles, and this is 32.6 light years away. So you'd be doing 32.6 times 5.88 trillion miles, and that'll tell you how far away this star is. So it doesn't look as bright to us because of its great distance away from the Earth. If it were as far away as Antares, people would not be able to see it without a telescope. Stars produce their own light, but planets and Earth's moon shine light differently. Instead, they reflect the sun's light. Absolute magnitude, like apparent magnitude, is also used to describe the brightness of these reflective bodies. To be consistent, they are measured when the visible side is fully illuminated, such as during a full moon. So the Earth looks bright if you're out in space. You're able to see the Earth not because it emits its own light, but because of it reflecting the light from the sun. Now, you are able to see city lights from space. You are able to see electricity from space. But the Earth as a whole, you're able to see from space because it's reflecting light from the sun. Same thing with the moon. We are able to see the moon because the moon face is reflecting the sunlight off of it. And that's why we get moon phases as well, because it has to do with the position of the moon and the shadow that the Earth casts on the moon because of the position of it between the moon and the sun. Quick fact. Antares is the brightest star in the constellation of Scorpio. It is classified as a red supergiant with a diameter of several hundred times larger than the sun. Even though its temperature is lower than the sun, Antares shines about 10,000 times brighter. Pretty amazing. And it's amazing we have technology to be able to know that these types of stars are even out there and how large they are. This cluster of stars is one of the largest inside the Milky Way galaxy and is located about 100 light years from the center of the galaxy. The different apparent magnitudes can easily be seen. So just in that picture right there, you can see many different size and colored stars. And so you can see their apparent magnitude is very different based off what we can see, not with the naked eye from Earth, but with high-powered telescopes. And those are in completely different galaxies. Pretty amazing. So you do not have a lab to do today with this work. So next time we're going to be going on to star populations and talking a little bit more about star clusters and how stars begin and what they do in space and what their jobs are. So I will see you next time.